Okay, today we're going to talk about eigenvalues and eigenvectors. In general, the equation that we're interested in is this one, ax equals lambda x. Here A is an n by n matrix. X is a vector in Rn, and lambda is just a scalar. Okay, so we're interested in finding solutions to this system, and if we can find solutions, then x is said to be an eigenvector, with the caveat that x cannot be equal to the zero vector. As you look at this system, clearly if x is a zero vector, then there's a solution, and it doesn't matter what lambda is. So we exclude that from consideration. Lambda here is said to be an eigenvalue. We have seen one example of this prior to this point. Let's scoot over here just for a minute. In the last section on Markov chains, we had the transition matrix M, and to get from one state, let's say xk, to the next state, we multiplied M times xk, and that gave us the state at time k plus 1. And in particular, we were interested in determining if, for a particular matrix, there was a steady state vector. Right? And the steady state vector is one where you apply the transition matrix to it, and you end up back where you started. So m times x is just equal to x. And if you compare this system with our eigenvalue system here, then you can see that they look similar. And in fact, if we write this one as mx equals 1 times x, then they look very similar. And what we have here is that m has a steady state vector if 1 is an eigenvalue of m. So when we're looking for steady state vectors, we already are saying, well, we've got an potential eigenvalue 1. Does it have a corresponding eigenvector? If it does, then there's a steady state vector. If not, then there is none. If you recall, the way we solved that system was to bring the x over to the other side. So we ended up with mx minus x equals a zero vector. And then we factored out the x. So let me do that. So we factor out the x. Remember, we ended up with m minus the identity times x equals the zero vector. And so then we just had a simple homogeneous system to solve, okay, where this is our coefficient matrix. We need to compute that first, and then we just solve the homogeneous system. We're going to use that same approach in finding our eigenvalues and eigenvectors. So over here, if we do that same thing, bring the lambda x over to the other side, then we have this system, and then factor out the x as we did before, and we need the identity matrix in here as we did before. Since A is a matrix and lambda is a scalar, we can't subtract lambda from A, so we multiply lambda times the identity matrix, and then we end up with a matrix here in a homogeneous system. So remember, we want to find solutions where x is not equal to the zero vector, right? So let's think about what that means. It means we want to find non-trivial solutions to this system. And then we need to think about, well, how do you find non-trivial solutions to this system? What properties must the matrix have for this system to have non-trivial solutions? Well, this happens when A minus lambda I has at least one free variable. Right? We need at least one free variable to generate non-trivial solutions to this system. So then let's think, okay, well, when does this matrix have at least one free variable? Well, that would mean that it is not invertible, right? Means that A minus lambda I is not invertible, right, from the invertible matrix theorem. And one way to get your handle on a matrix that's not invertible is to look at its determinant. So we know that the determinant of A minus lambda I has to equal 0, right? Because if it's not invertible, that means its determinant equals 0. So if the determinant of A minus lambda I equals 0, then that means it's not invertible, which means that it has at least one free variable, which means the system will have non-trivial solutions. So our first step here is to determine values of lambda so that this system has non-trivial solutions. And so we need to look at this determinant and then go from there to figure out what lambda is. And once we have the values of lambda, then we can compute the corresponding eigenvectors. So our plan of action looks like this. Step 1 is going to be find lambda such that the determinant of A minus lambda times I is equal to 0. And then step 2 will be to solve A minus lambda I times x equals 0 for each lambda found in step 1. Okay, so that's what we're going to do to determine our eigenvalues and our eigenvectors.